In this video, we'll learn about combining lists with other lists to make hierarchical structures that we'll call trees, and the recursive processing thereof. So we've seen three different ways already of combining lists with other lists. We've seen cons, we've seen the list operator, and the append operation. So if we make two lists here, define x to be the list 1, 2, and define y to be the list 3, 4, 5. So two different lists, and let's try combining them with the various ways. So let's define A as the result of appending x and y. We can define B as the result of combining them in a list. And we'll define C as the result of consing x and y together. So we have three different combinations of these two lists. So it helps if I type it properly. Define C. So we've got three different ways of combining these different kinds of lists, but let's look at what happens with each of them. So A, which uses append to join these two lists, we get a flat list. It takes all of the elements from list 1 and conses them to the front one at a time, as we saw in the previous video. So this gives us back a flat list with no definition beyond just the elements in there. B, which was the list of two lists, we can see we end up with a list with two elements, where each one of those elements happens to be an inner list. And C, which uses cons, we've seen this example before as well. What happens when we join two lists using cons is we create a pair where the first element points at a list and the second element points at a list as well. Now the second element, the CDR, is supposed to point at a list, so the second part here looks normal, but the car typically points to just a terminal element, if you will, or a primitive element, as we've seen. So because it's pointing at a list here, we have one object in our top level list is a list, in the case of the list 1, 2, and then we have three other separate objects representing the individual elements from the second item in our cons. So three different ways of combining these lists, and we can see the box and pointer notation for each of them. So if we cons two lists together, we create this pair where the first element points at a list and the second element points at a list as well. So we effectively get a top level list where the first element is itself a list. Whereas if we use the list operation to join two lists, well, we create a list where each item, so the car of each one of these pairs, points to one of the arguments to that function. So the list 1, 2 is the first argument, and the list 3, 4, 5 is the second argument. We can see that list there. And we can see, because we use the list primitive here, or the list operation, each one of the lists in there, the ones that we passed in as well as the one that it created, all are proper lists. They all terminate with that null character. So when we're combining these lists in these different ways, we're creating these hierarchical structures. And we consider these to be trees because they represent, or they can be represented by, rather, a tree diagram. So using our cons example here, we can see a tree diagram representing that instance. And similarly, using the list function, we have a slightly different tree diagram here. So in these tree structures, each list, each internal list, corresponds to an internal node in the tree. So we have the top level list in both of them. I think the list one's probably easier to see, where we had two elements that were each lists. So this first element here, 1, 2, branches off to become a different internal node because it's still a list, it's internal. But then when we reach the primitive items, those all correspond to leaf nodes. So when we consed a list onto another list, the first element was itself a list, and the remaining elements were just terminal nodes. So we have one internal node, not counting the root there, in this whole tree. So let's take a quick practice here. Let's define a quick tree and see if we can't structure out the diagrams and the trees in our whiteboard app. So let's define T to be the list with the list 1, 2, 3, and then a 4, and then the list 5, 6, and the list 7. So we run this code real quick, we can see what is the value of T, and we get this structure here, which corresponds pretty directly to what we typed. So let's open up our whiteboard and see if we can't draw out the tree structure. So the tree structure starts at the root node, which is just a top level list, which looks much like our output here. So I can actually copy the text from that. And let's actually put that at the top of our tree. There we go. So that's the top level node. Now in this list we have three elements. We have the list 1, 2, 3, the item 4, and then the list 5, 6 with the list 7 inside of it. So if we branch this out, one for each item here, then this first item is the list 1, 2, 3. This second item is the element 4, and this last item is the nested list 5, 6, and 7. And then for each of those, we create branches as well. So for 1, 2, 3, it has 3 items. So 1, 2, and 3, which are respectively 1, 2, and 3 as terminal values. 4 is not a list, so it's not an internal node. It is a terminal node. And 5, 6, 7 has 3 items. So 1, 2, 3. Let's make that a bit longer. Where the first item is a 5, the second item is a 6, and the last item is the list 7. Now, because this is a list, even though it only has one element, it counts as an internal node, which has a single child, which is the element 7. All right, so that gives us the tree diagram for this list structure, but we can also create the box and pointer as well. So with the box and pointer, the question is, well, since we used a proper list function here, this top level thing here should look like a list structure, that is to say that linked list set of pairs and pointers. So let's create some boxes here. So for creating a linked list for this top level list, we can see from our tree diagram that there's exactly 3 elements in that top level list. So we'll need 3 boxes, 1, 2, 3, where each one of these boxes corresponds to one of those branches of our tree. So we got a pair, which points to here. Let's just do that. And points to there. And some sort of external pointer telling us how to get to our actual item. Okay, so the first item in this list is itself a pair. So we need another box here. Oops. Another box here, which corresponds to list 1, 2, 3, which again has 3 elements in it. So 1, 2, and 3. And let's draw these out. Oops. Close enough. That goes there. That goes there. And now each one of these has a single element 1, 2, and 3, so we can just draw 3 lines down here, where the first one points to a 1, the next one to a 2, and the last one to a 3. Oops, 3. Right, so that's the first set. The next child in the top level list is just the value 4, so we can just make that a terminal node here. But this last one, 5, 6, 7, has to point to a list again because it is a pair. So we'll create a box out here. Diagram's going to get a little bit messy. So this is again a list with 3 elements. So 1, 2, and 3. Hopefully that's close enough. Okay, we need our line again. And that's the end of that top level list once we have this all set up. So that ends at a null pointer there. Now this is a set of pairs, so let's split all these boxes and connect them all. Okay. Now the first element in this list is a 5. The next element in this list is a 6. And the last element in this list is itself a list with 1 element in it. So we need a pair. Okay, where we have a single item. So it's a pair that's terminal. Doesn't have a full list there. And its only child here is the value 7. So our box and pointer would look something like this. And now from this list, we can actually start using, or sorry, from this box and pointer diagram, or possibly from the tree structure, we can actually start to use the same operators that we would use on any flat list in order to access the different elements of the tree. Right, so if we wanted to, for example, access the, let's say the 1 from this list, we start at the top here, we take the car, and then the car again gives us the 1. So if we say the CAAR of t, that gives us the value 1. If we want the 4, we take the CDR and then the car, just because it's in the top level list. So that would be the catter of t. That gives us the 4. If we want this 7, well, we take the CDR and the CDR again. Then we take the car of that, which gives us this inner list. Then the CDR and the CDR again. And then we take the car of that. So the CADDR of t is going to give us that list here. Right? So it says CDR twice, then take the car. So that's here. And then if we take the CADDR of that, so the CADDR of the CADDR of t, that brings us here. So 2 CDRs, a car, 2 more CDRs, and a car. And if we want just the value 7, we can do all of that and then ask for just the car of that. So all of the same operations that we learned for dealing with flat lists still work on these upper lists, provided that these lists are all proper lists. As say that all of these lists end with a null terminator, so that we can run through the same recursive operations as well without having to worry about weird structures coming into play. So once we have these tree structures built, we can apply a recursive approach to processing all of the different elements. So for example, if we wanted to traverse a tree just to display all the elements of our tree, we could create a function to do so that is a recursive function that recursively says walk through each one of these elements in the tree, and it works very similar to how we would deal with a flat list. We start with the head of our tree, or the head of our list, and we CDR down through the list, pulling the head off our list and walking down the remaining elements. The only difference here now is when we remove the head from our list, we can't assume that it's a primitive element, because the thing that's at that spot in the list might be a list itself. So all of our two-case problems, that is, say, all the code that we created that just had a single base case and a single recursive case, now ends up having three cases: a base case and two recursive cases. One recursive case for if we're dealing with a primitive element, and one if we're dealing with a list. So as a simple example, let's define a traverse function. Traverse some sort of tree. We'll call it T for simple. And now as I said, there's three different conditions. So the first condition is our base case, and that's that we've run out of elements to process. And the base case here works the exact same as it does in any other list processing algorithm. So the idea is, do we have a null list or a null tree? Let's say if we're looking at the end of one of these branches, then we're done. In this case, since we're just traversing the tree, we're going to print the elements as we explore them. So once we get to the end of the tree, there's nothing else to do. So I'm just going to leave this blank. This has essentially no value. It says do nothing. For all the other items, for all the other steps that aren't this empty list, well, then we need to check, is this thing a list or is it a primitive value? If it's a list, then we need to traverse through that list the way we would have traversed through this top level list. If it's a primitive value, then we can just treat it as we would treat any other value, in this case printing them out. So let's ask, is the thing we're looking at a list? So is the car of our tree currently a list? So if this is our tree here, we're asking, is the element stored in this first block a list? And if we follow that, we can see, well, sure enough, it is, right? This list primitive actually just checks, is this thing a proper pair? So is it a pair that the CDR points to something else that is also a pair? All right, so we check, is the car of this tree a list? And if so, well, then we have to do two things. We need to process through this car, right? We need to print out all the values down this branch, but we're not done traversing this top level tree either. So we're going to call traverse on the car, which is itself a list, and we're also going to call traverse on the CDR, which in this case is also a list. So two steps here. So we call traverse on the car of T and traverse on the CDR of T. Now note, we're using a cond statement here. So even though we have two separate expressions in the body of this condition, that's okay because there's an implicit begin statement. If you don't like implicit things in code, it's a good instinct to have. You can say begin here to make it explicit. And that just says do these two things. And again, we're going to do some side effect programming, so it might seem a bit odd. This entire function is just going to display things to the output, so it doesn't look as clean as some of the other examples will, but it does simplify everything for us, or give us a nice baseline to start with. So either we're dealing with the empty list, in which case we do nothing. We're dealing with an element that is itself a list, in which case we want to traverse that element as well as traversing everything else. But if it's neither of those things, then we're dealing with a primitive element. So we're, let's say, here in our list. We want to say, I want to process this 3, which in this case just means display the 3. So in that case, the car of T is just a primitive element. We can just display it, car T. But we also still need to traverse the CDR still. Right? Think if this was just given a flat list, we'd want to still print everything out. We just wanted to go through each individual element. We'd print the first one and then traverse to the rest of them. All right. And again, we have an implicit sequence here, but we can say an explicit one by adding the begin statement again. Purely optional there. So let's test this out. Let's run our code. We have this tree already built, so let's try traversing it. If we say traverse t. This should walk through the tree one element at a time. There's our tree there. So it should walk through essentially this box and pointer and print out each one of the values as it gets through each step. So if we run our code, traverse t, and we go, there we go, 1, 2, 3, 4, 5, 6, 7, and then true. The hashtag true here is just because it eventually has to return something, so the default value there is just true. Right, but notice it does print out all the values, and it also does so in depth first order, right? It prints out all of this subtree before coming back up and going through the remaining other subtrees. So it walks all the way down here, prints out 1, comes back up, 2, 3, and then down to 4, then 5, then 6, and then finally 7. All right. Let's see another example of tree processing. Let's try scaling a tree. So if we assume all of the elements in our tree are either lists or numbers, then we'll pass in a constant factor and multiply every number in that tree by that constant factor. However, we can't just multiply every element in that tree because some of those elements are themselves lists. So we have to process through that tree part by part, very similar to how we just traversed the tree. Checking to see if the thing we're dealing with is a list, then we can continue to traverse, or if it's a primitive element, in this case a number, in which case we would multiply the value and keep it back in the tree. So let's see that. So let's define a function called scale tree, takes in some tree t and some constant factor. Okay. So as with other recursive algorithms, we know we're done when we're at a null here. So if I say cond null t, that means we've reached the end of one of these branches, whether it's whether the entire list is just, imagine this was the entire list, 1, 2, 3. We reached the null, we've processed through the entire flat list. On the other hand, if you can think back to how traverse worked, we're going to be branching over the cars and CDRs whenever we have a list. So the traverse will come down into this branch and then eventually reach that null, but it'll also traverse across the CDR and eventually reach this null as well. So these nulls are sort of terminal to that part of the process, but not the entire process. We end up creating this branching tree structure with some repetitive recursions or some backtracking that ends up processing through the entire tree. All of that is to say, if somebody does ask us to scale an entire tree by some factor, but then they passed in a null tree, what should we return? Well, to scale all of the numbers in an empty list is trivial. We just give them back the empty list. All right. Now, let's say, for the sake of argument, they gave us a tree that wasn't all empty. Again, two things could happen. Either it's a primitive element, number in our assumption, or it's a list. So let's ask, is this thing a list? Sorry, is the car of this tree a list? If it is, then we have two things we need to do. We need to traverse through the car, so going through all of these elements and scale them, and traverse through the CDR and scale those. So we're going to do all the work on both of those, but in this case our result isn't just displaying to the terminal. We want to have some sort of value come out of this whole process. Specifically, we want to have a tree that looks exactly the same structure as our input tree, but with all of the numbers multiplied by some constant factor. So if we're taking elements apart using car and CDR to take the front half of this tree and the back half, if you want to call it that, if we're separating them with car and CDR, then we can join them back together using cons. So we need to say scale tree the car of t by some factor. We want to say scale tree the CDR of t by some constant factor. Both of these are going to return scaled lists or scaled subtrees, the car being this one, 1, 2, 3, and the CDR being 4, 5, 6, 7, everything there. So all we need to do is create this pair here again to join the results back together. That is to say, we just say cons those two things together. So again, if we're carring and CDRing things apart, if we want them back in the exact same place they were, then cons is the reverse operation. So we can just use that to join our trees back together. Okay, so that's what happens if we have a list as our primary element. We traverse both the car and the CDR and then cons the results. Now, if the item we're looking at isn't null and it's not a list, that means we're assuming it's a number. You can do some type checking here if you want as well. But we're going to assume at this point it's a primitive element. So what we can do is the actual work that we set out to do, which is multiplying, oops, bracket times, the car of t, which is, as we just determined, not a list, So we can multiply it by some constant factor. Okay. If we multiply the car of t by some constant factor, we still need to process the CDR of t. So we still need to say scale tree the CDR of t by some constant factor. And again, since we took the car and CDR apart, we want to join them back together into the original structure. So we say cons those two things. So to recap, if we reach an empty list, we just return an empty list. And that's going to be from all of these. If we reach an empty list here, it's going to return an empty list back there. Similarly down through the base case in this part of the tree where we said search through the car. It's eventually going to reach this null list. Then we'll cons on 3 times whatever our factor is, and then 2 times, and then 1 times, etc. Okay, so that's our null case. Then we have 2 other cases where either the car of our tree or list is a list or it is not. Otherwise, this thing looks exactly the same as the map. And actually, if you just delete this, I'm just going to cut it rather than delete it. This code here is exactly the code that we had for our map function. Go back to the code from the last video and you'll see this is exactly the same thing as what we did when we were scaling things. Possibly I've reordered the parameters, but other than that, it's the exact same design and the exact same structure. The only difference now, since we're dealing with a tree, is the first element in that list might be a list. So we have to ask, is it a list? If so, process that list the exact same way we were processing the top level list. All right, so let's test this out. So we run our code and say scale tree. We still have t there defined, so let's use that. We'll multiply it by a factor of 10. And we can see we get the exact same structure of tree. So instead of 1, 2, 3, we get 10, 20, 30, then the list 40, and then 50, 60, 70 all together. Now, as you might imagine, this scale tree function can be generalized into a scale map function as well. So, or sorry, a map tree function as well. So you can say define, I'll call it tree map just to be consistent with, I think, the notes. So define tree map over some t with some function f. Right. So this does pretty much the same thing. So we have some cond that asks, is our tree null? If so, return the empty list. Ask otherwise, is the car of our tree a list? If so, then we need to process both parts, both the car and the CDR, and then cons them together. So we'll say tree map, the car of t by f, and tree map, the CDR of t with f. Right, so we cons those together, and that gives us the result there. And then the thing that actually does any of the actual application of this function f to the elements in our tree is our secondary recursive case here, where it says that the car of our tree is not a list, so we can just say cons f onto the car of t. So apply this function to the first element in our tree, cons the result of that to the result of processing tree map across the rest of the list, so CDR t. So exactly the same as scale tree, but instead of assuming multiplication by some factor, we're just going to have some general purpose f that can be passed in when we call the function. So we can, for example, say tree map t with lambda x times x, for example, the square function, and we get the exact same structure of tree, but now all the elements have been squared. All right. That's pretty much it for this video. So processing trees is much like processing flat lists. The only difference is we can't assume that the elements in that list are in fact primitive elements. We have to first check, is it a list? If so, process it like a list. If not, process it like an element. That's it for this video. We'll see you in the next video where we'll talk about a brand new kind of data, the symbolic data type.